The next concept we'll learn is the concept of mean, variance, and standard deviation. These are very, very simple terms which you might have already encountered in your probability course or in your 12th grade. These are very simple concepts. Let's understand what they mean intuitively and where they fail, why are they useful, and things like that. So let's do one very simple thing. What is a mean? Mean basically means that, okay, if I'm given observations, so let's take your setosa petal lengths, right? I have 50 observations. Let's call them x1, x2, so on, so forth, x50, right? So let me call them setosa petal lengths, okay? So it's a set of 50 observations, right? Now, what is the mean of all of them? Mean of all of them is, mean is often written with the Greek alphabet mu, right? So mu of setosa petal lengths is nothing but you sum each of them, x1 plus x2, so on, xn, and divided by the number of values. So n here is nothing but 50 because you have 50 observations, right? More concisely, you can write this as summation I equals to 1 to n xi multiplied by 1 by n, right? So this is what mean means. Mean is basically simply the simple average, right? Now you might ask me, what is the use of mean? Why are we learning about the mean here? So now let's take a very simple question. So what I've done here is, let's look at the code. I'm just printing the means of NP is basically nothing but your NumPy. NumPy has a simple function called mean, and I'm printing the mean of petal lengths of setosa, versicolor, and virginica, right? So this one, and this one. I'll come to what this is in a second. Just hang on. Just ignore that. My first, third, and fourth. Okay, first, second, third, fourth. Just ignore the second one. I'll come to what it is in a second. But just this is setosa's petal lengths. This is versicolor. This is virginica, and this is versicolor. Now, by just looking at the means, by just looking at these three numbers, no plots, nothing, I can quickly tell you that setosa typically tends to have a very small petal length, while the petal lengths of virginica and versicolor are closer. I'm not doing any plot here. I'm not using any plot. By just looking at means and means of these three things, the first takeaway, by just looking at these three numbers, setosa, virginica, versicolor, by just looking at these three numbers, forget this number for a second. I'll come to what it is in a while. Okay, by just looking at these three numbers, I can tell you that setosa flowers tend to have a much smaller petal length as compared to virginica and versicolor. And virginica and versicolor have petal lengths, of course, versicolor petal lengths typically on an average are smaller than virginica, but the difference is not as significant as with setosa. That's the first takeaway. But I have a question. What if, okay, so this is clear, right? This is clear on what a mean is. But I have one problem with mean. So for example, I have 50 values, right, for setosa. Let's take all of your setosa values. We know that from the diagrams above, we know that the setosa values lie between 1 to 2. And the mean value and the central value or the mean value is 1.464. What if there is one, so we are taking these readings, right? Suppose somebody entered a wrong value. Okay, so let's assume we have the 50 flowers, we have the reading of all the 50 flowers, x1 to x50, right, of setosa petal lengths, right? Now, let's assume somebody did one more reading. Somebody took the 51st flower. For that 51st flower, they mistakenly entered the number as 50. The petal length as 50, which is like crazy high. 50 centimeters petal length is like a massive sized flower, right? Suppose this error happened because somebody entered a wrong number or the data got corrupted, 100 other reasons. Okay, so such a data point is called an outlier because all numbers lie between 1 and 2, but there is one observation. There is one observation at 50. Now, such a point is called an outlier because it is not a norm. It is not normal to find a value like that. And this error could have happened because of many reasons. It could be because somebody entered it wrong, because data got corrupted, or somebody instead of putting numbers in centimeters, they put in millimeters, 100 other things, right? Now, when I have one error like this, what happens to mean, right? So if you look at the second line, what I'm doing here is I'm taking the mean by appending all the values in the petal length, all the 50 values that I have for setosa's petal length, and I'm appending that array with a value of 50. So I have 51 values here, such that I have my x1 to x50, and my 51st value is 50 itself. Now when I append such a value, now the mean of this is 2.4, which means one simple number by one simple error could corrupt my mean a lot. My actual mean is actually 1.464. Just because I had one error, my mean now became 2.415. This is a problem, because if you have one mistake or one error or one outlier, your whole mean could jump drastically. And this mean tells you nothing about, because 50 points lie here, right? And only 1 point lies here. But this 1 point has corrupted my mean so drastically. So mean has this problem, because what is mean? Mean is nothing but summation of all the numbers divided by 1. This is what the mean is, right? And the sum could become extremely large if I have one extreme point, right? If let's assume all my numbers lie between 1 and 2, but only one number exists which is extremely large. Let's assume it is 1000. My sum will increase drastically, right? Because of one mistake. So mean has this fundamental problem that because of one outlier or one error, your mean can increase drastically. Okay, that's something that we have to take care of. And that's important because we'll revisit this problem with mean and come up with new ways of measuring using things like median, percentiles, etc. Okay, having understood what mean is, so what is mean telling us? Mean is telling us about central tendency, if you want to think about it. Mean tells me what is the average sepal length, what is the average petal length for setosa, for virginica and versicolor are like. It's telling me something about the average behavior of the flowers, right? But there is one more observation, which is, let's look at it like this. There is another concept called, okay, just like mean measures the central tendency, as I just told you right now. There is something called as spread. So let's understand what spread means intuitively, graphically, before we go and write the mathematical equation for it, right? So here, if you look at these plots, right? For these plots at least, for these plots, your mean for setosa was 1.4, which is roughly around here, right? Your mean for petal length. So let's go and look at what the means for versicolor and virginica are. From what I remember, 5.5 and 4.26. Okay, let's just put them on the plot. Okay, so it's about 5 point something, 5.2, and this is about 4.5. I'm just putting these numbers roughly. They're not the exact means. The table below certainly has the exact numbers. Now, one thing you'll notice is we know what is the average value like, right? Which is good, right? But the problem here is, here if you notice, your setosa flowers do not have, the range of setosa flowers, petal widths, is much thinner than the range that you have for either versicolor or virginica, right? So if you look at these histograms or PDFs, what this width here represents something called spread. So spread in simple English basically means what is the typical range, or what is how widely spread. So if I can somehow measure this spread, right? I know what is the central tendency. If I can also measure the spread, it will give me a good intuition on how wide these points are spread. So if I know that spread is small, right, that's very useful because I know that most of my points are around 1.4. If I know that spread is wide, so for example, let's look at it like this, right? So let's assume I have 1.4 and let's assume my spread is 0.5, some measure of spread. Okay, what does it mean? It means that most of my points lie between 0.9, right? And let me add spread to 1.4, which is 1.9, right? So if I just add spread to that, I know that most of my points lie here, which is extremely useful. Now let's assume for this, the spread is 2, which means most of my points for versicolor. So even though my mean is 4.5, if the spread is about 2, I know that they typically lie between 2.5 and plus 2 for this will be 6.5. That doesn't mean that there are no points outside 6.5. It just is a measure of how widely spread your distribution is, right? So imagine if I have to understand about distributions without plotting. Remember, all your computer plotting tools are only 40 to 50 years old. Prior to that, you didn't have tools to plot like this. People used to plot with hand. So instead of plotting, are there numerical approaches which can help me understand how widely? Here we are seeing the plot and we are saying, okay, your virginica is much widely spread. And of course, your virginica is much more widely spread than your versicolor. Your versicolor has a much wider spread than your setosa. This we are looking at it from a plot and saying this. Imagine if we didn't have a plot and we wanted to get some numerical representation of spread, right? So what I've used as spread in simple English can be thought of as variance. So there is something called variance of a bunch of numbers. So so let's take our setosa petal lengths. We have x1 to x2 to x50, right? So we said mu, or the mean, is nothing but the summation of all these values from I equals to 1 to 50 and multiplied by 1 by n, or n equals to 50, okay? Right? Now, this is my mu. So what is spread? Spread basically says how far are my points typically from my mean, right? So variance is often defined as summation of across all points, take each of my points xi, subtract mean from it, right? What this is telling me is, if this is my mean, right? If this is my point x1, it says what is the distance of, let's say this is my point x2 and this is my point x3. So it says how far away is each of my points from mean, okay? But this distance could be positive or negative, right? To make it, but we want to measure distances, right? So let's just square it so that all these numbers, because this distance could be 2, this distance could be -1, so on and so forth. If you just square it, you basically get all positive values, right? Now variance basically is defined as summation over, or the sigma over each of the points when you subtract it with the mean and square it. So this is the formula for variance. Intuitively, let's see what it's doing. It's basically saying what is the distance of each of my points from the mean, right? Of course, what is the square distance, because I'm squaring it, right? So this is what variance means. Now what I can do quickly is, what if I take the square root of variance? What will that look like? That will look like square root of summation I equals to 1 to n, if I have n points, right? X minus mu, sorry, xi minus mu whole square. If I just do, so this is variance, right? Sorry, I think I did a small mistake earlier. The variance formula is the average value of, I think I forgot to put this 1 by n earlier, right? So this is the formula for variance. So what it's saying is, what is the average square distance? So this is averaging, right? This is averaging. Variance is saying, what is the average? So it's always useful to read formulas in English because they give us much better and richer understanding of what it is. This is nothing but average, right? This is square, right? This is distance. So variance is nothing but the average of, so average is nothing but sum and division. So this is the whole average. It is the average square distance of each point from the mean value, right? And square root of variance is nothing but standard deviation. So let's understand this term. It's basically saying what is the deviation, what is the average deviation of points from the mean value, right? So if your standard deviation is small, you know that the spread is small. Spread, the word spread that I used is basically a simple English word, but what I actually meant mathematically is standard deviation, right? So let's look at what is the standard deviation for each of this. So standard deviation, thankfully, is very simple. You get .std, np.std, you can just give it, which gives us the standard deviation. Now here is an important thing. So if you look at the standard deviations so this is again, setosa, virginica, versicolor. The setosa has a much lower standard deviation, which means it has a much thinner spread or much lower spread, while your virginica has slightly higher and versicolor still higher. But the spread's here. So by just looking at means, so neglect this again, as I told you earlier, by just looking at means and standard deviations, I can quickly come up with some very, very interesting thing for you. So let's do it, right? So if my mean, so okay, let's assume you just gave me this, let me try to interpret them. If my mean was 1.464, if my standard deviation was 0.7, which means most of my points lie in the interval of, or at least a good number of points, or a majority of my points, I shouldn't say most, I should just say majority of my points lie between 1.464 minus 1, so this is 1.46 minus 0.17, and this is 1.46 plus 0.17. I know that most of my setosa flowers, or a large number of my setosa flowers, lie here, right? Similarly, what about my virginica? My second one is virginica. My virginica mean is 5.5, right? So let's assume this is 5.5, and I have a variance of 0.54, which means most of my points lie between 5 and 6. Most of them, not all of them, certainly, right? What about my third one, which is versicolor? The value is at 0.46, right? 0.46 lies here. Sorry, the 4.26 is the mean, right? And this is how my intervals are, right? So what you have done right now is you've taken the mean and you're saying the spread is this much. If the spread is wide, it means that points are more widely spread. You'll find points from all across the board. If the points are if the spread is low, they're much more densely grouped, right? So by just looking at mean and variance, I can imagine this plot in my head. That's the advantage of means and variance. Again, the problem with variance or standard deviation is just one outlier can corrupt the whole number, just like mean, right? Because at the end of the day, the variance formula is still same, right? You basically have 1 by n, which is averaging, right? You have xi minus mu square. If you have one xi which is very, very far away, its distance from the mu also will be very, very high, right? Which means there will be one point xi for which this value will be very, very large, which means your variance also can be corrupted by one mistake or one outlier or one error.